Hello everyone, I am Andrey Leonidov from Lebedev Physical Institute, Moscow, and Moscow Institute of Physics and Technology. And the subject of this short lecture is elementary particles and particle accelerators. The subject is, of course, enormous and will be able to, so to say, scratch the surface a little bit. Still, I will try to convey you some key thoughts or key facts about the field. And we'll start with looking at modern accelerators. The biggest and the fanciest one is the Large Hadron Collider at CERN. This is Geneva, Switzerland. This is an enormous ring in which protons are accelerated and proton beams are colliding, and also nuclear beams are colliding, for example, lead nuclei. And on this ring you see several orange points. These are experiments, for example, CMS, central muon solenoid, ALICE, ATLAS, and LHCb. Both CMS and ATLAS are experiments where proton-proton collisions are studied, while ALICE is studying high-energy nuclear collisions, and LHCb studies some special properties of weak interactions. And you also see that this is not just one ring, but a system of rings that starts with so-called booster. So the primary accelerator, and through the complicated system of rings and pipes, the accelerated protons are finally fed into this very large ring. And one very spectacular thing about this collider is that the magnets that keep these charged particles inside are superconducting. So it's a very complicated device, and it was very difficult to put it into operation, but it all paid off, because you might know that the famous Higgs boson was found at this accelerator. Let me show you a picture of how it looks. This is an LHC tunnel, and you see how large is this construction, so that people are actually riding bicycles inside it to get from one point of accelerator to another. Now, once again on experiments, CMS and ATLAS are experiments for high-energy proton-proton collisions. ALICE is an experiment for nuclear collisions, high-energy nuclear collisions, that studies the so-called little bang that we'll discuss later. While LHCb is for something special that I won't touch, at least I won't touch in the present lecture. Now, just look how complex are the detectors. These are the ATLAS and CMS detectors at the LHC, and you see figures of people drawn, so that the height of the detector, you see it on the left, the height of the CMS detector is 25 meters. This is an enormous construction. The purpose of this construction is to detect particles that were created during the collision, and when created, they propagate not along the beam, but at some angle to the collision axis. And all this enormously complicated construction serves for testable detection of these particles. Both ATLAS and CMS detectors are planned so that they can study very rare events, in particular events where this, once again, this famous Higgs boson, the particle that provides masses to all known particles, so that this Higgs boson is born. Now, two other colliders, just for illustration. This is the relativistic heavy ion collider in the USA, RIC, in Brookhaven, in the Brookhaven National Laboratory, not far from New York. And again, you see that this is a circular collider that can accelerate both protons and nuclei, like LHC, but the energy of collision is much lower. Here, the energy of the center of mass collision, so that the center of mass is the situation where particle meets symmetrically, so to say, is around 200 GeV. GeV is an convenient measure of mass and energy at high energies. Just to have a scale, the mass of a proton is approximately 1 GeV. And this is a collider where a new state of matter, the quark-gluon, the free quark-gluon system, was first detected. Here you see again that it's not one ring. You see several other items here. LINAC is the primary linear accelerator that feeds particles into the booster. The booster feeds them into the old ring. AGS is an old accelerator at the site, and only after AGS the particles are fed into the main ring. The difficulty is that you have to produce bunches of particles and keep the particles in the batch close together, which makes collisions effective. There is also one accelerator that will soon be in operation in Russia, in Dubna, 100 kilometers from Moscow. This collider is called NIKA, and here you see its scheme. And here, once again, the booster, so the initial acceleration, comes from the old accelerator that was built in the 60s of the previous century, called nucleotron. And from this nucleotron, the particles are fed into the main ring. The characteristic energy of this collider is not that big. Its main purpose is to study the properties of baryon matter. Now, when we discussed a little bit how colliders look like and what modern colliders do exist, now we turn to a discussion of what we know about elementary particles, and we start with matter. And here you see Greek letters, and these Greek letters are very meaningful. Let's start from the upper bullet, the so-called leptons. For example, the leftmost, the upper one is electron neutrino. This is a massless particle, and the lowest in this within this bracket is electron. The first is muon, neutrino, and muon, and the last is tau, neutrino, and tau. Meson, and the upper guys are chargeless, the charge is 0, and the lower guys have charge -1, as you know from school physics. You know about electrons, and muons and tau mesons have the same charge, but they are heavier. Electrons are of course part of matter, but most of the mess that we see around us come from protons and neutrons, and to build these we need so-called quarks. And here we again see three items that physicists call doublets: up and down quark, charmed and strange, top and bottom, if you look from left to right. And then to the right you see something strange. The electric charge of these guys is fractional. The charge of U, C, at T and T is 2/3, and the charge of D, S, and B is -1/3. And now you can say we have never heard about particles with fractional electric charge. Because atoms, for example, they consist of nuclear and electrons, and nucleus and electrons, and nucleus consists of protons and neutrons, and protons have charge +1, and neutrons have charge 0. And just to explain how this happens, now both protons and neutrons are called hadrons, from Greek word denoting strong interaction. And then you see, for example, that proton is a composition of 3 quarks, U, and D, and by adding their charges you see that the proton charge is indeed +1. Neutron is UDD, so the charge is 0 as it is. And then to just as an example, two other hadrons, now called pi mesons, pi plus and pi minus. And now the line above D means that this is an antiparticle. An interesting feature of what we know about matter is that charged matter is accompanied by an existence of charged antimatter. Now, we don't observe antimatter because when matter meets antimatter, they annihilate, they just disappear. And the history of universe is such that matter managed to decouple, and that's why what we call matter and we ourselves exist. This is an interesting problem that we cannot go in any details. Add a little bit mystery. This is how proton looks like in truth, so to say. You see a star-like thing connecting, or a vertex that connects U, and D, these 3 quarks. And now these springs contain special particles that are called gluons. Gluons because they glue together these quarks. Quarks are not observed as free particles. We observe them only in combinations with integer electric charge. And you see that proton is not just something glued by them, but glued in a very special way. And this is an interesting theoretical challenge, because certain properties of protons and also neutrons related to the existence of this vertex have still to be clarified even right now. Okay, let's move a little bit further. Now, one of the deepest things about matter that we know is that this matter is not what physicists call invariant with respect to left and right. First thing that I have to say is that fundamental matter is massless. So all fundamental particles are massless. So they propagate, a massless particle propagates somewhere, and you can attach clockwise or counterclockwise rotation to a direction of propagation. And when it's counterclockwise, we call the particle left, and when it's clockwise, we call the particle right, and this cannot change. This is a fundamental property. And now it turns out that one interaction, the so-called weak interaction, I'll explain it a little bit later, one of the interaction operates only with left components. And that's why you see that the bricks here, they are drawn separately for left particles and right particles, and left components and right components meet only to organize mass to the particle. And when participating in weak interactions, right particles stay away and do not participate. This is one of the deepest mysteries about nature that we know. It's not clear how this happened. What is the origin of this difference between clockwise and counterclockwise? There is a special property of the particles that is attached to this counter or clockwise, which is called spin, the magnetic moment that is characteristic of a particle, but it's a strange magnetic moment because the particle is point-like, and there is no current that so we don't have current that creates it. Still this moment exists and determines very fundamental properties of matter. So this is what we know about matter. Now, if we stay within this picture, these guys will never see each other because we have not explained how they interact, how they feel the presence of other particles. To explain this, we introduce something that is called interaction, and there are agents that are responsible for organizing these interactions. The simplest is the photon that you have heard about from school. And so, for example, electron can emit a photon, or the photon can hit the electron, and the elementary fact about interaction is the existence of this vertex, electron photon or muon photon. Any charged particles can emit photons, and another particle can serve a recipient of this photon. And this is how interaction is organized. Photons can exist on their own, as we all know from the existence of light. Now, this is electromagnetic interaction. Another kind of interaction, the weak interaction, is the interaction that, for example, converts neutrino to electron. Just remember these doublets from the previous slides. You see that these particles interact by changing their nature, so to say, within the doublet, so that neutrino can become electron. When neutrino becomes electron, you have to balance the charge. And so and here you see how this charge is balanced. the same for U and D quarks. It's very interesting that one can also have neutral current, so neutrino can stay neutrino but still emits some object which is called a Z boson. And finally, a strong interaction that is responsible for the existence of hadrons and nuclei. Here, quarks have a special charge, which can take 3 values, and this interaction operates in such a way that in most cases the charge is changed, and so the particle that is responsible for this, it has, so to say, 2 color. This charge is called color, and so you see that this gluon G and this wavy line denotes gluon. The wavy line in the last bullet denotes gluon. It has 2 color indices, so it's responsible for the processes when quarks are changing color, and this is the interaction that keeps this fractionally charged particles together. The phenomena, this phenomenon is called confinement, because quarks are confined within hadrons and cannot escape from them. Let's use this knowledge to describe the simplest process of annihilation of electron and positron into muon and anti-muon. This example is interesting because it illustrates the fundamental thing. 2 things matter: conservation laws and energy. If you have enough energy, you have produced as many particles as you like. For example, in nuclear collisions at LHC, thousands of particles are produced. All this is explained by the famous Einstein formula E equals mc squared. So that energy and mass is something that is equivalent. If E is very large, then if it is permitted by conservation laws, for example, by conservation of electric charge, then many particles can be produced. And so in this particular process, you see that electron and positron disappear. You see they're incident horizontally in this picture, and a pair of muon and anti-muon are created at some angle to the collision axis. Now, this is a cartoon that explains what happens in very simple terms. This is approximate, as I will show you a little bit later, but this approximation is quite good because electromagnetic interaction is weak. In each of the vertices, we have a number which is 1/137. So it's the probability of this process is not very large. And so you see what happens. We have E minus and E plus that create what is called a virtual photon. It's not a real photon, it's a mediator, and which then decays into a pair containing mu minus and mu plus. An interesting thing is that you see arrows at antiparticle lines that are oriented from the collision point. This is an interesting fact about antiparticles, and you will know more about it if you study quantum field theory. So I'll leave it as an interesting question for further studies. Now, just to come back to what I told you about counterclockwise and clockwise, I'll just tell you that if we prepare the incident beams so that only specific states, or left or right, are prepared, now the outcome of the collision, of this collision, will depend on the states. And now to calculate what happens a little more precisely, we have to take into account additional processes. Here are all cartoons that explained how to compute the first correction to the picture, to the cartoon that we had. These cartoons are called Feynman diagrams, and these diagrams were invented by a genius, Richard Feynman, one of the authors of quantum electrodynamics, and you see many interesting possibilities. For example, this virtual photon, before decaying into muon and anti-muon pair, this is the leftmost cartoon, upper line, it creates a virtual electron-positron pair, this circle in between, which then decays back into the virtual photon. And you see that, for example, that final particles can interact, all sorts of possible cartoons. It's very important to have a systematic theory that allows you to understand what are the appropriate cartoons for a given process. And this science is called quantum electrodynamics. This was the first operational quantum field theory explaining nature. Quantum field theory is a science that combines special relativity and quantum mechanics. And when you create such a combination, you see that this theory should necessarily describe processes in which many particles are created. Now, we have these cartoons. The next question is, what do we do with these cartoons? How do we calculate something that is interesting phenomenologically, something that can be measured? And this leads us to the notion of cross-section. So, let us consider two colliding beams. Just imagine two bunches of particles within the accelerator that are incident at each other. Now, just as an estimate, it's clear, right, that the number of collisions is proportional to the number of particles in the first beam, to the number of particles in the second beam, and of course to the area of intersection of these bunches. If they don't touch each other, for example, nothing will happen. If they fully overlap, then these collisions of two bunches will create a lot of individual collisions of particles inside the bunches. So n is proportional to a product of an A and B and A, where A, once again, is the area of intersection. Now, to characterize the number of specific events we are interested in, we introduce a new quantity, sigma, and you see how we do this. We ask what is the fraction of the available effective area that corresponds to production of something that is interesting to us. And so in the second bullet, you see that the number of interesting events in sigma is sigma over A, this ratio, and of course it's proportional to NA and NB. And you see that just to keep dimension balanced, sigma should have a dimension of area. And the final formula at this slide is the formula for the sigma, which is just n sigma over NA times NB times A. The quantity sigma is called a cross-section, and this cross-section is a fundamental characteristics of process, and this is a quantity that is of utmost interest, the quantity that has to be calculated. For example, if we were interested in the process of electron-positron annihilation, we should calculate a cross-section of its annihilation to something. This is a fundamental characteristics. Now, a couple of words about units. The basic unit for a cross-section is called barn. One barn is 10 to minus 24 centimeter squares. Barn might seem like an odd word for this. Now, historically, it was coined by the great physicist Enrico Fermi, one of the people who were behind the US nuclear bomb program. But even before that, he invented key things on weak interactions. So here's what he said: neutrons in nuclear reactors hit uranium targets as easily as hitting the broad side of a barn. And indeed, the cross-section of neutron uranium-235 scattering is about one barn. Now, just to understand what are the relevant scales, at the LHC, the cross-section of proton-proton interaction is approximately 0.03 barns, or 30 millibarns. And the cross-section of Higgs particle production at the LHC is 4 times 10 to minus 11 barn. So you see that this is quite small, and you can estimate yourself how many collisions should you create to be able to observe such rare processes. Now, all this results in measuring this cross-section, and this is one of the famous cross-sections, the ratio of E plus and minus to quark anti-quark pair to cross-section of E plus and minus annihilation to muon anti-muon, and the line is a prediction of theory, and you see that the theory that we have ideally predicts the data, so it just comes through the data. One interesting thing about this plot is that from this plot we see how many colors do we have. So how many special charges does each quark have? And from this picture, from this plot, one can immediately see that this number is 3. Now, a little bit on how we learned about very fundamental properties of weak interactions. This is the annihilation again of a plus and minus to a pair of what we call intermediate bosons. You remember these bosons, that these bosons are responsible for electron-neutrino conversion, for example. And here are the cartoons of the processes that theoretically participate. And two extremely interesting diagrams are B and D. The diagram B tells you that the interaction carriers are interacting themselves. And the diagram D says that there should be another particle called Higgs particle that participates in this process. Now, an interesting thing is when we measure the cross-section of this process, so we just identify this final state and see how often does it happen, can we learn something about this interaction? Can we convince ourselves that all these mechanisms are really operational? Here's a very, very, very famous plot. And you see the blue curve is when we take into account all the mechanisms. Dotted red curves are when we omit some of them. And you see that in particular ZWW vertex, it is confirmed experimentally. And here it's just a famous example of how people became convinced that that some specific theory is a right one. There were many stories like this, and this journey took almost 50 years or even more, and this journey came to its completion, or to what we think is a current completion in 2011 when Higgs particle was discovered. Now, the last thing that I wanted to tell you about is on heavy ion nuclear collisions. What could be an interesting point to study there? It turns out that in a certain sense, matter created at the early stages of this collision resembles the matter created during first just when our universe was created. As I told you, many particles are created. Here's an illustration of such a collision. Thousands of particles are created at the LHC, and these are studied by Alice collaboration at LHC, as I told you. And now, when we try to describe this process, then as illustrated by these cartoons, so first, when these nuclei meet, the first thing that is created are very strong gluon fields. Then the system expands, and these fields become individual gluons, because of course gluon fields are composed of gluons, much like electromagnetic fields are composed composed from photons, and so this field decays into particles, which form something that is sometimes called quark-gluon plasma, a new state of matter. And then this system of particles presumably equilibrate. We don't know whether this really happens, but it might be that to a certain extent the matter created resembles a color analog of electron positron plasma and photon plasma we know from electrodynamics. Then this, of course, we don't have walls, and so this thing still expands, and these quarks and gluons, some of them get together and form hadrons, because, as I explained you, these particles cannot exist in free state. So they form hadrons, and finally these hadrons flow into detectors, and from characteristics of this flow we can look back and try to analyze the properties of this primordial system, and the whole process is sometimes called Little Bang in analogy to the Big Bang, the process of creation and evolution of the universe. And there are some similarities in these two pictures, but also some distinctions. Big Bang is a phenomenon that was very slow. Cosmological expansion is very slow, while Little Bang is a very fast one. That's why even now we are not very sure that the system of quarks and gluons created in these collisions can equilibrate. So this was the last point I wanted to tell you. This elementary particle, high-energy elementary particle physics and high-energy nuclear physics is a tremendously exciting thing. Theoretically, the theories that describe these phenomena can really be considered as masterpieces, and it still remains a very good subject of interest to young people who want to know how matter at its depth is organized. Thank you for your attention.